Hi, we're Group 3 of the Large-Scale Software Development class at Virginia Tech. We did a multi-copter simulator. I'm Emery Barlow.
Michael Hespenhide. I'm Lloyd Cole.
And now we'll give you a brief overview of our project.
The goal of this project was to create some sort of event-driven library, that is, programming object which programmers can integrate into their projects to accomplish some more complex task with a few simple function calls. Our group chose to create a simulator for multi-rotor quadcopters. Using a few simple function calls, a programmer with no knowledge about the details or inner workings of a quadcopter, AI, physics, or PID algorithms can create the basis for a powerful and expandable simulator. This demo breaks down into three large parts: the user interface, or example application which uses our library, simulator process, which is an instance of the library, and a shared memory space used to pass data back and forth between the two. A shared memory space was chosen so the user interface could access simulation data without interrupting or interfering with the simulation that's in progress. In the next few minutes, we'll give a brief walkthrough of these pieces, starting with the user interface.
Which has 8 engines, all arranged geometrically around the center. We have a map on the right side which shows where the position of the multicopter is at any given time. It's in a 6 meter by 6 meter room simulating its position, and it shows a nice little graphic of where the engines are. So we're going to start it up. So whenever you click on the map, it uses a key painter to determine the coordinates you clicked, sends it back to the simulation, and will compute the engine data to get to that position accordingly. So there's a variety of supporting widgets to go along with this. In the middle you see an altimeter right here, and that shows where the multicopter is currently floating in the air. You can change that using this little widget on the left side, and you'll see a corresponding change of the altimeter. Depending on which way the multicopter is traveling, it will affect the heading indicator, which is below the altimeter. As you move it around, you'll see it go through all the coordinates on the heading indicator. Another thing to take note of is in the bottom left corner there's the engines, and that shows the thrust at any given time out of a percentage of 100 of what each engine is doing accordingly. So as you move around the multicopter, you'll see the engines that are trying to tilt it in that direction will end up doing more work. Or if you raise the altitude suddenly, they'll all start to take the load to get it up to that height. In the top left, you'll see some various telemetry about the project, and that's just for debugging or any other various output you want to use it for. It's expandable with the widgets you have for this, so you can add new things such as vertical, artificial horizons, or other widgets, whatever you may wish to choose to do so. And there's velocities, there's pitches and rolls, the headings, the current altitude as well as the target altitude, which you set manually.
Our project used a small bit of artificial intelligence. The goal of this was to calculate the target pitch and the target roll that would allow us to get to our destination. The destination was passed to the AI object through a function. The current coordinates for the copter was also passed to the AI object through a function. The AI object then used a PID controller for each of the pitch and the roll. What the PID controller did was the further away from the destination the copter was, the greater the pitch and or the roll was. And as it got closer, these two values decreased significantly, thus preventing overshoot. I can pull up the user interface here and run our simulator. And if I give it a target destination by clicking in the GUI, you can see it slowly starts to move towards that destination. As it gets closer, it slows down. The velocity slows down. And eventually, when it reaches the destination, it goes into a hover state.
The underlying architecture of the project was built to be very modular and more like the operation of an actual multi-rotor copter. The simulation object is created in the multi-copter simulator process. Here, you instantiate the simulation objects using the library. You choose the number of motors, the weight, gravity, arm length, and all the other simulation variables. The individual motors are actually independent processes started by the simulation process. The shared memory space is created using Q shared memory, and a public key, which the GUI can use to attach to the memory space and get access to all the data shared there, as well as pass the altitude values that the user enters in the GUI back to the simulation. Every few milliseconds, the simulation process sends a D-bus broadcast message out to all the motors. The motors, which are only aware of their location on the copter, but not what any of the other motors are doing, adjust their throttle point to do their part to achieve the target angles. So, if a message to tilt forward is received, the frontmost motor will decrease thrust, and the backmost will increase its thrust. All of the motors also act to increase or decrease thrust to maintain the target altitude. Each time they receive a new target message, they calculate their new thrust values, like we talked about above, and send a response dbus message to the simulation process. The simulation process then calculates how all of these thrust values will affect the location of the craft and updates the shared memory space with the new x, y, and altitude information. And then the cycle repeats. Using our library is very simple and requires only basic familiarity with object-oriented programming and just the knowledge of the existence of shared memory spaces. These are the steps in code needed to create and start a simulation. First, a simulation object is instantiated with the desired number of motors. Next, several simulation variables are customized, such as gravity and arm length. Next, we connect to the shared memory location using the same key used elsewhere in the code. In this case, a simple ASCII string, public shared memory. Finally, an example of how to read from and write to the shared memory is shown. It's up to the user to decide how to utilize the data the simulation provides in the shared memory space. There, you will find everything from throttle positions to pitch and roll values to current and target X and Y values, among much more. You can find all of our code, comments, and notes, as well as contact information at my personal GitHub. Please, feel free to use and improve our code in your own projects. If you do, please let me know.